Hi guys, Audrey here. So today we're going to discuss the case of infinity times zero with L'Hopital's rule. So let's look at this first example. We have the limit as x approaches pi from the left of x minus pi times cosecant of x. So first thing we want to do is plug in that pi. When we plug in pi to x minus pi, clearly we get 0. Now the question is, what is cosecant of pi from the left? And in this case, it's probably going to be a good idea to use our reciprocal identities to think of this in terms of 1 over sine of pi from the left. Now we know that sine of pi is 0, so this is like 1 over 0, which means that it's going to be either infinity, negative infinity, or does not exist. Either way, it's giving me that infinity, so we can think of it as infinity right here. If I want to go and figure out which one it is, remember that it's a good plan to look at the graph of sine. So sine, we know, looks something like this, where that's pi. I'm on the left side of pi right here. So on the left side of pi, we can see as x approaches pi, my y values are getting closer and closer to 0, but they're positive while they're doing it. So we're above the x-axis as they're getting closer and closer to 0. So this is actually 1 over 0 from the right, which tells us that this is a positive infinity. Okay, so we got that this was 0 times infinity. Now remember, in the 0 times infinity case, our goal is always to take it and turn it into either 0 over 0 or infinity over infinity. And the question becomes, which is a better thing to turn it into? Well, when there are trig functions involved, because we have those reciprocal identities, it's usually a good plan to bring the trig function to the bottom. So in other words, what I want to look at here is this is the limit as x approaches pi from the left of x minus pi over cosecant x. Well, we already saw right there was 1 over sine, so this is like over sine x. So bringing that trig function to the bottom will definitely leave you in a form where taking the derivative is easier, doing L'Hopital's rule is easier than if I had brought that x minus pi to the bottom for cosecant x over 1 over x minus pi. So this is clearly the easier case. Let's do it. So now when I plug in, I've turned this into sine of 0 is 0 to 0 over 0. So we're going to apply L'Hopital's rule. HR on top of my equal sign there. Limit as x approaches pi from the left. The derivative of the top is 1. The derivative of sine is cosine. So I have 1 over cosine x. I plug in, I get 1 over cosine pi. And I know that cosine pi is equal to -1. So this is 1 over -1 to give me a -1 as my final answer. Okay, so for our next 0 times infinity problem, we're going to have to think about arctan a little bit. So we have the limit as x approaches infinity of x times pi over 2 minus arctan x. So in this case, when I plug in, clearly, when I plug in infinity to x, I get an infinity here. But what's happening with that arctan? So we're just going to take a second to remember what the graph of arctan looks like. It kind of looks something. We have a negative pi over 2 down here. We have a pi over 2 up here. And it kind of looks something like that. So what we can see is that as x is going to infinity, my arctan function is getting closer and closer and closer and closer to pi over 2. So in other words, this is like pi over 2 minus pi over 2, which, hey, is 0. So this is infinity times 0. Now, since we have the infinity times 0 form, we want to turn this into 0 over 0 or infinity over infinity. The question is, which one is a good function to bring down? In our previous question, we saw that bringing that trig function down was useful because of our reciprocal identities. We don't have similar reciprocal identities for inverse trig functions. But more than that, my options here are to either have pi over 2 minus arctan x over 1 over x, or x over 1 over pi over 2 minus arctan x. So I'd have to bring that whole pi over 2 minus arctan x down to the bottom. And we can see that clearly this one is the more complicated one. We're going to stick to that other one. Bringing that x down to the bottom as a 1 over x is definitely going to be the easiest way to approach this problem. So we'll have the limit as x approaches infinity of pi over 2 minus arctan x all over 1 over x. And now when we plug in, we get 0 over 1 over infinity, which is 0. So I can apply L'Hopital's rule. So I get the limit as x approaches infinity. Now remember, pi over 2 is constant, derivative of a constant is 0. So that's just 0. Derivative of arctan x, 1 over x squared plus 1. So this is negative 1 over x squared plus 1 over negative 1 over x squared. So now, if I were to immediately plug in that infinity again right now, I would get 0 over 0 again. But that doesn't mean I should use L'Hopital's rule again immediately. Remember what we've said. Always make sure that you simplify before you just immediately go to L'Hopital's rule again. So I'm going to simplify. Those negatives are going to become positives. And then that x squared can be moved up to the top to give me x squared over x squared plus 1. So at this point, I have two options. My option 1 is to take the big stuff. Here we are approaching infinity. We do have a polynomial over a polynomial, so we can just be like, hey, look, this is the same thing as x squared over x squared. So that x squared is my big stuff, and that x squared is my big stuff. So I'll end up with the limit as x approaches infinity of x squared over x squared. Both of those x squareds cancel out, and we get that this is just equal to 1. So that's my first option, but I also have this second option. My option 2 is to use L'Hopital's rule. So I'll end up with the limit as x approaches infinity. The derivative of the top gives me a 2x. The derivative of the bottom also gives me a 2x. And notice those both cancel out, and I end up with a 1 either way. So either one of those options is perfectly valid. I would say using L'Hopital's rule to check your work is actually probably the better thing to do, as opposed to actually using it to do the work. Because a lot of times when we have these polynomials over polynomials, you can end up having to do L'Hopital's rule over and over and over again before you actually get anywhere. Taking the big stuff is definitely the fastest, most efficient way to approach these problems. Anyway, that's all. Bye, guys.